Welcome back, everybody, and to this session on resampling techniques, and in particular the blocking method, which is the one which is used for calculations where you have lots of data. So the kind of topic today is a quick reminder, very quick one from last week. In particular, just a quick reminder of the central limit theorem and bootstrapping. And I just remind you of the notes from last week. And then we are going to say a little bit more about the motivation for the resampling techniques. And in particular, we're going to look at the blocking method. And when we're done with that, so hopefully we will just use this first lecture on that topic. And when we are done with that, we are going to look at something which is called the one-body density. And after the break, we will say something about the optimization with the Python, and also a little bit about C++ optimization. So mark also that the notes which you have for this week, they contain much more material than what we will cover, in particular when it comes to C++ parallelization. I know that it seems to us now that most of you will actually use Python. So is there anyone here in the audience who is still running in C++? Okay, we still have people. Oh, good, good, okay. Because when I talked to Daniel and Håkon, they said that well, nobody was programming in C++. Okay. Maybe that's the case, yeah. Maybe that's the case. Okay, that's good. So again, just a quick reminder of what we discussed last time. So the simulations which we have can normally be treated as computer experiments. And that's particularly true for Monte Carlo calculations. And the results can then be analyzed with same statistical tools as you would have when you analyze experimental data. And as in all experiments, we are looking for expectation values and an estimate on how accurate they are. The cases which we have when it comes to errors is the statistical error. And that's something which we then can estimate. I mean, systematic errors are much nastier and much more difficult. So we will just stay with the statistical errors. Now, one of the things which we discussed last week, but we didn't give you the equations for why this is the case. This is the calculation of what is normally called the autocorrelation function, which is tightly linked with the covariance. And the covariance measures the correlations between data points. I'm going to show you some examples with simple random number generators and how we can estimate the degree of correlations. Now, when you set up the mathematical expression for this, what you end up with is a double loop over the observations. So if you're running let's say a calculation with 1 billion Monte Carlo cycles, you know that for every cycle, you collect a contribution to the expectation value of the energy and the energy squared, which you then use to calculate the variance. In this double loop, you wouldn't like to calculate, in this loop, you wouldn't like to calculate a double loop. Because that means that if you have 1 billion cycles, you would have to evaluate 10 to the 18th contributions. And you don't want to do that. So what this blocking method is, it's a method to circumvent the problem of you having to evaluate a double loop. So that's the basic message. And you will see that now through the equations which we get when we are setting up the equations for the autocovariance or the correlation functions as it's normally often rewritten in terms of. So that's the basic kind of overarching motivation. And I'm going to just take this one out a little bit and bring it up like this. Because so what we did last week was to derive the central limit theorem. And then we used that one together with Bootstrap to actually use Bootstrap to demonstrate the central limit theorem. And one of the things we assume then is that we have an individual experiment where the subscript I stands for experiment I, a measurement you're making. And we're assuming that all the events which we have are stochastic variables which are independent and identically distributed. So with that, we could define the sample mean of that specific experiment. And then we could then define the sample variance. What we did next was that we defined M experiments or M measurements of the type I. So that means that the total average is now the sum of all the experiments. And then the total variance is something which then is given by these experiments, which we have, the average of each experiment, minus the total average. So what we assume then is that these quantities are also independent and identically distributed, and they have their own distribution. And what we found then in the central limit theorem, if these events x of I, the mean values, are independent and identically distributed, then in the limit where n goes to infinity, the distribution for the mean of all the experiments is something which approaches a Gaussian distribution. So we could now, and this is what we are going to do in order to calculate the expression for the final sample variance, is to replace this x here, which you see here, with this quantity, and then we're going to break it down in terms of the individual experiment. And when we do that, in terms of when we rewrite this quantity in terms of the individual experiments, then we are going to get a double loop. And it's that double loop which we don't want to evaluate. So let me switch quickly. So just keep this expression in mind. We are going to bring it up on the whiteboard again. So let's now just switch over to the whiteboard and take a closer look at the expression which you would get for the correlation part. And that's the term which we normally cannot neglect. So let's switch to the whiteboard and remind ourselves about some of the mathematics here. So what we did was to define these variables. So we have the total mean of m experiments. And we label that as an x, and that is a 1 divided by m. I'm going to put a bar on top of it. And this is a sum over I equal 1 up to m. And this x of I was then defined as the average value for a given experiment, where we now run n total experiments. So that could be something you're running in a series of days. So you repeat the same experiment again and again, just to accumulate data. So you have 1 day, which is day 1, day 2, day 3, etc., etc. And these experiments were then rewritten in terms of this parameter, this variable xij, so where I stands for the specific experiment. And then we could define the variance of these experiments in terms of this quantity here, of I equal 1 up to m. And then I have this x of I minus x. So this should be an uppercase letter. So in the limit where m goes to infinity, if these x's, the mean values of an individual experiment, if they are so-called independent and identically distributed variables, this approaches a Gaussian distribution, the distribution for the total mean value, as we demonstrated last week with the central limit theorem. Now, what we can do now in these calculations, I'm just going to introduce a simple shorthand here. So I'm going to define, if you now look at this quantity x of I minus x, so this x of I minus x here is something which we can rewrite in terms of the individual ones. So we have 1 over n, so this is squared, and this is 1 over n, and then we have a sum over j equal 1 up to n, and then we have x ij, and this is minus x like that. Now, we can lump these terms together again. This is just the definition of the x of i's. So we can bring that into that expression. Now, there is another thing which we also have. So this is one quantity which is defined in terms of the total mean and the mean of each experiment. But we could define what is called the total sample variance. And I'm just going to call this sigma squared. And this is given by 1 divided by mn. And this has a sum over in equal 1 up to m. And j, this is just us setting up the standard expression for the variance minus x. So what we want to do now is to relate this total sample variance to this sigma m here, which is now given by the mean values. And what I will do then is, if you look at this quantity which I defined here, this one, this is a quantity which we can just lump together. And it's actually normal when you do this calculation to center the data. So if you look at this expression here, and then we replace it with this one, which I'm just going to call for an xij tilde, because I've just subtracted the mean value. Then I can take this expression which you have here, and it's not very difficult to see that this one can then be rewritten as, so if I do that, this is this sigma m squared is going to be given by 1 divided by m, and then I have to square this quantity here. So I have a sum over, so there's a sum over I equal 1 up to m, and then I have this squared terms, which then are given by this xij tilde, and these terms have to be squared. Okay? So I'm just manipulating expressions now. That's the only thing which I'm doing. So this one can also be rewritten in terms of this xij tilde. Now, when I now open up this second equation, what I get then, so there's a 1 over n here, obviously, because I'm just plugging in the expression which we have here. So this term here is the one I'm squaring now. And keep in mind that what you have here is just a constant. So I can just put that one in here. And then when I sum it up n times and divide by n, then I just have the same constant again. So what I do then when I square it, I open it up. So I get 1 divided by m and n squared. And then I'm going to have a diagonal term. So there will be still a sum over I up to m. And then I'm going to have a diagonal term, which is xij tilde squared. And then I take all the non-diagonal terms. Now, the non-diagonal terms, as you know, they will be symmetric as well. So I can actually just lump this together into a sum over I equal 1 up to m. And then I can have a sum over j less than k. This is a double sum. And then I have an xij tilde, xik tilde. So this is just a rewrite of that square term which we have here. This one. So what I can do next is to, if I assume now that these are if these quantities which we have are independent and identically distributed, you can then show that in the limit m and n become large, that this term should be equal to 0. This term which you see here is normally called the autocovariance or just the covariance term. And this measures the degree of correlation between an event at j and an event at k here. And these can be different positions or different types of events. And you will see later that this kind of measure of these correlations is actually an important estimate of whether a random number generator is a good one or bad one. And what you will disappointingly see is that all pseudo-random numbers, they will have a term like this one, which is not 0. So this is simply because the random numbers we generate, they are actually not true random numbers. They are normally what we call pseudo-random numbers, and they are generated by a deterministic algorithm. And one of the typical one is called a linear congruentials, which is often a manipulation of the modulus operation, which means, again, that there will be correlations in the random numbers we generate. So in principle, you would like to have random numbers which are true random numbers. Unfortunately, that becomes time consuming if you want to use true random numbers. And that means that since you are running billions of Monte Carlo cycles, the generation of these random numbers, you have to strike a compromise between true randomness and some kind of pseudo randomness. So the hope then, when you look at the random number generator, is that this term is as small as possible. And we are going to test these equations now with the uniform distribution. And hopefully this will show you why these kind of manipulations we are doing now are relevant. And you see now one important aspect. When we calculate the variance, we are actually just evaluating if we now put m to 1 and we just have a huge loop here, then the variance will just be given by a single loop. This term here, on the other hand, is a double loop. And that is often the problem, which we want to avoid. Okay, so let's move on a little bit and take a closer look at how we can rewrite this term. So if we now make a comparison with what we have here, you see now that the first term is actually this term here, divided by n, whereas the second term is going to contain something which is different from that. So we can rewrite this term here in terms of what we define as a total sample variance of n squared, plus this term which goes like 2 divided by m of n squared, and then I have a sum up to m, and then I have this double sum j less than k, and then I have my x j tilde. This is now centered already. So for those of you having taken a course in machine learning, you know that's pretty common to center your observations. So this is just a centered variable. It's also introduced by me by simply a sheer laziness, because it's much easier to deal with a more compact form than just adding the mean value all the time. Now, what you can do now is to rewrite this one, and the standard way which this is done, and which serves as a kind of entry point to the discussion of the blocking method. So if you now look at this last term, what you can do is to define a parameter d, which is the distance between j and k. So you can simply rewrite that double sum by defining a new quantity. So what we are going to do then is to define a quantity, which you in the lectures I call f of d. So I define that simply as 1 over m and 1 over n. And there is a sum over I equal 1 to m. And then there is a sum over k equal 1 up to n minus d. And then you will see that this is something I now can rewrite simply as a sum over this d. And this has a d k plus d. So instead of having this j, I'm introducing this d, which now represents a distance between two observations. So what you're assuming then is that if these observations are far away from each other, so I generate a random number now, and then I wait 1,000 steps. So that means that the distance will be 1,000. Then I would assume that these two random numbers should not be correlated. So that is normally used as a test of random number generators. So the thing which is useful to note then is then that with that definition, and pay attention also to the fact that if I put d equal to 0, then this f of 0 is just 1 over m, 1 over n, and then I have an I equals 1 up to m. and then I have a sum of k equal 1 and up to n. So this is x of ik squared. This is the same as that sample variance which I have. So what I can do now is to rewrite the expression which I had, this sigma m squared, in terms of this function fd. So I can rewrite it as a sigma squared divided by n plus 2 divided by n. And now I have a sum from d equal 1 up to n minus 1. So I invite you just to check that this is correct. This is just a rewrite of the variance of the means which we have introduced. So this term which you see here is normally called the autovariance or autocovariance, or just a covariance term. And that is 0 if you have data which are independent and identically distributed. But we don't have that in general. In general, because already from the very beginning, the random numbers which we generate produce some degrees of correlations. So what is common is then to define a new function. So we can actually this is f of d, right? So we can rewrite it like that. So what is common is to define a new function, which we call for k of d, which is given by this f of d divided by sigma squared. And this is called the correlation function. Now, this correlation function, we notice also that f of 0 divided by sigma 0 is the same as 1. So it has a specific value when d is equal to 0. So that would be k of 0. If I introduce that function, I can then rewrite this sigma m squared in terms of sigma squared divided by n. And then I have 1 plus 2. And then I have the sum of d equal to 1 up to n minus 1. And then I have this correlation function, k of d. And this represents the error which we have, or the error, or better, the contribution from correlations between the events. So if you go into that article about the blocking method, they would typically call this the error estimate. But in principle, it's not an error. It's an error in case you want your variables to be independent and identically distributed. If they are not, if there are correlations, you will have to evaluate this term and you have to take it into consideration. So what we're going to see now when we run the Jupyter notebook is the following. So when you make a plot of it as a function of the distance between a measurement, because now what we did was to introduce this distance here, which is to be seen as a distance between a measurement. What you will see when you plot this is something like this. So this function k of d, when we now look at the function at 0, so we can then have 1, 2, 3, 4, etc., up to many, many values of d. So we have 1 here. So that is one of the observations. Then ideally, we would like to have 0 for the rest, but we don't get that. So what you will often see is that this has an observation here, it can have a value here, it can actually turn negative. Now, keep in mind that the total variance is a positive quantity. So, but ideally, we would like this one to gradually disappear. So what we should see is something which goes slowly like this, and then approaches 0. So this is what you will get if you now run the calculations. This has a consequence then when we look at this quantity we call for sigma m. So when we now calculate sigma m squared, and we look at this as a function of this parameter d. So we have 0 here, 1, 2, 3, etc. What you will see then is that here we have this sample mean, which we can calculate directly, assuming that the quantities are not correlated. So just keep this in mind. This is an assumption that there are no correlations. So this is now given by this number here, which we can calculate simply in our code. However, this actually the covariance, you can show that that is a semi-definite matrix, which means that its eigenvalues are larger or equal than 0. So in principle, it's a convex function. This is a larger than 0 function. So that means that what we will get is something which goes like this. And then what we would like to, if you now look at this curve here, is to figure out when this stabilizes, when it flattens out. And that is going to give us the value which we want to use to calculate the standard deviation. So this will be our sigma m squared. Now, the blocking method is a way to figure out where this plateau kicks in by regrouping your data in blocks, where you just split your data in blocks by 2 every time. And then when you find that this additional contribution here, which now comes from this term of 2 divided by n of this kappa d, this is the correlation function of d equal 1 up to n minus 1, when this one becomes 0, that is when you can assume that all the data are essentially uncorrelated. So this is ideally what we want. So let's switch to the Jupyter Notebook and take a look at that before we spell out the blocking method and how that is actually, what is the philosophy behind it, and how we can actually achieve what you see here without calculating a double loop. So I can, and this is the big issue, I can calculate this one. There's no problem which hinders you doing that. But if you then go back to your Monte Carlo calculation, you see now that this term here is a double loop. So you would have a double loop over all your events. And if you have 1 billion Monte Carlo cycles, you would have to make 10 to the 18th evaluations. So inside your Monte Carlo loop, there would be a double loop. And you don't want to do that, period. So the blocking method is actually a way to perform the calculation of this quantity here without evaluating a double loop. Because at the end, so as I said last week, this sounds like a kind of strange thing. We are putting all these efforts into just getting this estimate and simply saying that we don't believe that this one is the best result because this is too optimistic normally. So we want to have a reliable estimate of the standard deviation. And we know that there are correlations in the data. Does that sound pretty clear? Do you see the main message why we do this? Okay, so let's, so it sounds like a kind of triviality. Why don't we just do a double loop? But you will see quickly that if you want to do a double loop, it's going to be expensive. So let's show you that and go to the Jupyter Notebook. So there is a simple code here in the Jupyter Notebook where we do that. So if we scroll down, essentially what you have here is what we did on the whiteboard. So this is a case now. So let me just reduce it to 1,000, because if you do 10,000 here, a double loop, you will see that that's going to be slow. And then since that's going to be slow, I may even be tempted to let time fly to crack one of my lame jokes. And you wouldn't be happy then. So let's do 1,000. So what you see here is just me using a uniform distribution. So what is the mean value of a uniform distribution? Anyone remembers that? 0.5. And you can calculate analytically the standard deviation, which is 1 over square root of 12. So that's the standard deviation. and you can calculate the variance. So you have a simple analytical expression for this. So when I sample only 1,000 points, I will not get 0.5. I will get 0.499 something or 0.500 something. Now, so what you see here, I'm calculating the mean values, the variance, and the standard deviation by just doing what I call the sample, the total sample mean and the total sample variance. Now here, I can actually calculate this autocorrelation function. So this is the second term, and you see here I run over J, and I run over K, and the only thing I do now, I take K plus J. So that's my distance between the 2 points, the 2 observations. So this is essentially me going back to that equation which you saw here. This, didn't I put it down here? Yeah, I defined it like this. So this is essentially the term which I'm setting up. And now I'm putting this m equal to 1. So in essence, what I'm doing is to calculate what you see here. And I'm calculating each contribution to this function kappa. So the kappa is what I'm calculating, yeah? No, this is just an exclamation that this is, yeah. So this is not the factorial. That's a good point, actually. This was me just putting exclamation marks everywhere, right? Like when you send a text message, it's always full of exclamation signs, right? You shouldn't do that. My daughter always teases me, and she says that it's only old people with exclamation signs all the time. Okay. So if you do this now, and we make a plot of it, this is what, so you see, we don't get exactly 0.5 because we have only 1,000 points. We don't get exactly the 1 over square root of 12 here. But what you see is a correlation function. And this is a correlation function as a function of these 1,000 measurements. And for this random number generator, you see now you have 1 here as expected, but then it's non-zero for all the other values. And this double loop, actually, you saw now this was pretty fast. If I now put this to 1,000, and I promise not to tell one of my bad jokes, but this is going to take a lot of time again. So you see now you're getting a better mean value. It's getting closer to 0.5. You would actually have to go pretty high to get it. But you see now that the calculation of the autocorrelation part is taking more time, because now you have a 10 to the power of 8 evaluation. So this took much more time than the previous simple case. And you see now that this is dropping slowly to 0. So since we Norwegians always like to tease the Danes, we would say that this looks like Denmark seen from the sea. Or if we want to, you probably heard about Holland, the Netherlands as well. This could be the Netherlands. Actually, you don't see the Netherlands from the sea because it's below sea level. Yeah, I think I told this story before. Okay, so let's now, so the whole thing now, if you look at this calculation, if you want to be trusted, you have to evaluate the correlations. Now, the thing is that what we want to do now is just to avoid calculating this double loop. And this is essentially the blocking method. This is a rewrite of the calculation of the autocorrelation part, period. So let's go back to the Jupyter notebook and set up some of the details. So what the method essentially does is then to transform the data. So what you do in the blocking method, so we have a data set which could consist now a set of observations, x1, oh, let's do the numbering since I kept this numbering from 0 to n. So we would have a set of observations which are given by this n up to n here. So these are the observations. And then what I'm going to do then is to split the data into blocks of 2, and then new blocks of 2, new blocks of 2, etc., etc. So what I could do now is to define a new data set, x prime, which now has n prime, which is equal to 1/2 n observations. But what I'm doing then is now that instead of having these previous observations, I'm going to have an x0 prime, which is going to be the original x0 plus x1 divided by 2. And then I have x1 prime, which is going to be x2 plus x3 divided by 2, etc. And then I can split this in 2 again, and 2 again, and 2 again. So it's pretty common then to set up the number of Monte Carlo cycles or Monte Carlo samples, the number of Monte Carlo samples. It's pretty common to set that in powers of 2. So what P could be some number like 20, 21, 22, etc. Because then I can keep splitting my data in these blocks of 2 all the time. So if you suppose now that you have, as an example, you have 16 data points. So I would have something like an x0, x1, up to x15. So that would be my original data set, which I will label in a generic way as an x0 of 0. So 0 here, the superscript is actually the original data set of 0, etc. So I'm just going to put that one like this. And then my next one would be given by the following. So I will now split the data. So divide by 2. That is n. So we have n/2. So we have less data points. And what we are going to find then is obviously that the total variance, you can actually show that, has to be the same. And the total mean value has to be the same. So these quantities don't change. But what you're doing now is that you're reshuffling weight between terms in the covariance and that sigma squared, which we looked at previously. So we're just reshuffling strength. It's just another way of rewriting the same expression for the variance. So what we end up with then is something like we have an x1 prime, no, x0 prime. So this is a prime number. So we will just label this as an x0 of 1. So that's the next data set, x1 of 1, etc. And this x, which we have here, which we now can write as an x of k of a sum of I plus 1, where we have an I and divided by some quantity which we are going to call d minus 1. So d is now the total number of blocks we are making. So what we have then is that this quantity is going to have a general formula here. So we would have 1/2, and that's, now let me just write this one down here. So this is going to be equal to 1/2. So just the mean value of 2k minus 1, and this has I plus x of 2k of I. So it's just the average of these two quantities. What you will see then is one thing is that the mean value which we calculate. So if we look at the mean value as the original 1 divided by n, and then we have this x of I, this is going to be the same. You can easily see that. And that will be given by 0. That is going to be the same as all the mean values mu of I, where this mu of I is just 1 divided by n of I multiplied with a sum over x, which we have here, of j of I. And this j goes from 1 up to n of I. And where now this n of I is actually given by the original n divided by 2 to the power of I. So we're just splitting the data in blocks which are equally sized, and that's why it's very convenient to set up the calculations in terms of a number of Monte Carlo cycles, which is given by 2 to the power of something, because then we can keep splitting the data. Till at the end point, we just have 2 data points. And these are actually 2 blocks, where one of the data points will contain half of the data and the other one, the other half of the data. Okay? You see the basic philosophy here? So you can continue, and what you will also see is that this quantity, which we called sigma squared of m, of these mu values, so when I take a mu of 0, that will always be the same as the sigma squared for the mu of I. So these are invariant quantities. It's actually not that difficult to show that. If you set up a simple example and you recalculate the variance and you recalculate the mean values, you will then see that these quantities are invariant under these changes, which they have to be. Because if you now look at the quantity which you have defined, that means this quantity here. If I split these in different ways, I should always get the same result at the end. So what I'm going to do now with the blocking method is that in a certain sense, we are going to recalculate this term and recalculate this term as a function of blocks. So when you do that, you actually have a recipe which you can use to set up these expressions. And the recipe which you get then for these quantities, and I see we are running a little bit over time here, let me just set up the expressions which you will have. So we will have something which is going to be a sigma of mu. So this is in invariant quantity. And it's going to be given by a quantity, and I'm going to define this subscripts which we have. So this n of k's, this is actually me having some problems placing. So this will be an n of k here, plus this 2 divided by n of k. And then I have a sum over h equal 1 up to this n of k minus 1. And then I have 1, and I have to explain what some of these terms. So this is just a number where I'm counting, and divided by n of k. And this is multiplied by a term, which I'm going to call mu of gamma of k of this variable h. And I will define what that looks like. And this gamma of k here, of a quantity which I'm going to call h, which I will label a little bit later what it means. This is the same as this covariance, which we defined earlier, of x over I, and then I have k here, and x of j plus h of k. So these are quantities which we can calculate, and what so this h here is actually the distance between a measurement I and a measurement j. That's the distance between 2 measurements, what I previously called for d. And what Flyberg and Petersen showed is that when you rewrite these equations, there is an analytical expression for this gamma, which I will put up after the break. And with that one, we can set up the basic algorithm. So let me just set that one up, and then we're going to take a break here. So this is now given, so if I write this as a k plus 1 as a function of this distance, this takes 2 possible values. So I have 1/2, and then I have a gamma of k, and then I have 2 times h plus 1/2 of gamma of k of 2h plus 1. This is the case if this h is equal to 0. And it has another term which goes like, so I'm not gonna derive these terms, I'm just setting them up. So I have a 2 of h minus 1 plus 1/2 of gamma of k of 2h plus 1/4 of gamma of k of 2h plus 1. And this is else. And that leads to this expression for the total variance, which is the quantity we want at the end, which is now given by a sigma squared. And let me put this as a k divided by this n of k, the number of points or blocks which we have, plus 2 divided by n of k. And this is the same as the quantity which I wrote up earlier, where we had a sum in terms of d, which is a distance between two measurements. And this is 1 minus this h, the distance, divided by this n of k, and multiplied with this quantity gamma of k of h. So what they did in the paper, because they didn't prove that this gamma converges to a fixed point when you increase the number of blocks. So typically what you would get would be something like this as a function of the number of blocks. And you would typically see when you reorder it, so with 0 blocks, we are back to the term which we call sigma squared divided by n. This should be our sigma m squared, the one we want. And for 0 here, with 0 blocks, this is just a full data set. We would have something like this. And then when we move to the next point, so I'm just going a little bit over time here. I hope you can forgive me. So this means that n of k, n of 0, is equal to the total number of points. So this is the quantity we start with. And then we move to the next one, where we have 1 here. And in that case, we have n prime, which is equal to 1/2 n. And then the variance increases. We go to the next point here, where we have n double prime, or n of 2 here, which is equal to 1/2 of n1. So this is quantity is also equal to n1. And in that case, we could get something like this. And what here? And then this would continue, and hopefully this would flatten out. And where it flattened out, that is where we would reach the final value for sigma m squared. So we are not going to go through the proof that it converges to such a flat line. This is actually given in Mario's thesis. So in the original article by Flyberg and Peterson, what they did was just to numerically find a region where you reach the plateau here. What Marius did was actually to give a formal proof that this is what happens. Yeah. Say it again. Oh, I don't remember. I have to look it up again. Yeah. It's actually 6 years since I read the thesis. I have to look it up. But that's actually, he was very dissatisfied when he saw the original article, and he wanted actually to prove it in a more rigorous way. Because what Flyberg and Peterson did was simply to rewrite this term, which I presented to you in terms of a double sum. They just rewrote that one so that every time you split it in blocks of 2, you reevaluate this term. So this term now, this one, which you have, is going to define this term. So that term changes, and then you reweight what comes in here. So you can show, and that is what Marius did, that this converges to the same as if you were to set up the full calculation here of this quantity here. So it's just a reordering of the points. and it avoids calculating a double loop. So that's the main takeaway message when you do blocking, that you want to avoid calculating a double loop. Yeah. Yes, yes. So I would just recommend that the codes which we have presented in the lecture notes, the codes written by Marius, that you could just use them. And then after the break, I'm just going to quickly remind you of the codes. And then Daniel is going to say something about parallelization in Python. And then we're going to look at parallelization in C++. So you will find the links and many other things to the blocking method in the Jupyter Notebook. And just to quickly remind you of the top-down approach, which we took last week. We have this Monte Carlo code for 2 electrons in 2 dimensions, interacting with a Coulomb interaction. And just quickly to remind you of one of the topics which you need to add to your code when you calculate the energy is that now you need to print out the energy, and you can decide whether you want to print it out for every Monte Carlo cycle, or you want to do this in blocks of, let's say, 100 cycles or 10 cycles or whatever. Because if you run 1 billion Monte Carlo cycles and you print every time, this will slow down your code and you would get huge files. So what many people often do is that they collect data after, let's say, 100 or 1,000 Monte Carlo cycles if you are running many calculations. And then when you have that, so this would be the Monte Carlo calculation as we discussed last time, then you can use the codes which we have. We have the code for the blocking method. And then this code will simply read in that data file. So if we just rerun this one, so this is actually pretty fast to run. And it uses the optimizer with the Broyden's method, which is added here in the BFGS. And this finds the optimal parameters first, and then it launches the big calculation. And you see now that I'm setting everything in powers of 2. So I have the root 2, no, the base 2, and then do power to the 19 for the 20 for the many you want to do. And in this case, you see now the energy is close to 3, which it should be. And this is the one when you start the parameters and you start the big Monte Carlo calculation. And then you would use that data file you produce as an input to the blocking analysis. And here you see the evaluation of the standard deviation. So all this kind of stress for just getting this number here, which is a small number, hopefully. But this is evaluated using the blocking method. Now, feel free to use these codes which are here and run a post analysis after you're done. Or if you want to write your own codes, feel free to do that. But these are typical things you would use as a post analysis in order to generate the last number here. And or you could alternatively do it inside your code and then just store things and not write to file. It's up to you how you want to do that. So this was one of the technical elements. So right after the discussion of one-body densities, Daniel will say something about the optimization in Python. And also, we have lots of material on how to optimize and parallelize with OpenMP. And the easiest case for those of you who program in C++ is to use OpenMP. So OpenMP is tailored to shared memory architectures, whereas MPI is something you can easily use with both distributed memory and shared memory. So a standard supercomputing facility, a high-performance computing facility, is normally a farm of PCs, and these PC can be very different. So it's often a heterogeneous farm of different PC clusters. And that means that the MPI is often the tool which is used to connect the different clusters of PCs. And you would often use a mix of MPI for the communication between the different PCs or clusters of PCs. And then you would use MP, OpenMP, or communication within a given PC where you have the same shared memory. Now, Monte Carlo calculations are very easy to parallelize because this is very much like you starting a main job, and then you distribute the labor to all the different nodes. And then you let these run independently, so every node has its own copy of the executable and runs this in parallel. And then at the end, you just collect the results. This is a very simple approach, and it's often called embarrassingly trivial to parallelize, or embarrassingly parallel, because this is actually the simplest case we can parallelize. So anything which deals with numerical integration is extremely easy to parallelize. So we won't get the time to go through everything today with OpenMP, but you can follow the instructions here and just implement the basic commands. There are several examples you can look up. So the parallelization itself with OpenMP is actually pretty straightforward. And the same also with the message passing interface. We're going to say a little bit about that. And there are also lots of hints on vectorization, which is worth thinking of. So this is something you get for free if you think a little bit. And you get it for free also with different optimizations parameters. So if you have a C++ code, you have different ways you can optimize your code. So you have flags, and one of the flags can be no optimization at all. That means that the compiler takes your program and it just translates it into code as you wrote it. And that can contain stupid things like including constants which you multiply with inside a loop, which are operations which you shouldn't do. You can actually just add a constant. So if you have a constant, you're adding to a vector. And if you do that inside of a loop with 1 million loop variables, you're just doing 1 million unnecessary additions. So you could simply make the operations on the vectors, and then outside the loop, you would just add the constant. So there are some examples in the notes here on things you should avoid. And then the compilers try often to optimize and vectorize with different flags, which can often give you a performance increase of a factor of 2 to 3, often, but just changing compiler flags without almost thinking. But that requires that you have avoided some of the pitfalls when it comes to hindering vectorization. So there's a long discussion there, and we may say something about it after Daniel has said something about Python optimization. But before we do that, I wanted to say something about the one body density. So let's just switch to the whiteboard again. So this one body density is a quantity which you will encounter in many body theories, many times. And it's often used as a simple way, a theoretical way, to gauge the role of correlations and the forces which are present. So suppose you have a given number of particles. So this one body density is something you would calculate after optimization. So you find the optimal wave function, which gives you the minimum of the energy. So you would, this is a post-analysis part as well. So when I say after optimization, this is when you have found the energy minimum and you have the wave function with the best parameters. So you would then calculate this quantity, which I'm going to write in terms of a quantity rho. And this is a vector in general. So you can integrate out particle 1, and you can replace R1 with just a variable R, because this is just a variable. But in our case, this is now an integral over all the other particles which are present. So this letter here, which you see, is my attempt at writing the letter R. And this is then multiplied with a wave function which you have. And this now depends on all the coordinates, R2 up to Rn. And you have found the optimal variational parameters. So I'm putting a hat on that, and this is squared. So clearly, this becomes a multidimensional integral in the same way as you evaluated the energy. So what you have from the calculations, you have this, and you have the mathematical form, so you can plug that in. But clearly, you would have to evaluate this with Monte Carlo methods as soon as you go beyond 2 free particles, because else it's going to be very time consuming. So in our case, if we stay as an example, if you stay in 2 dimensions, then this R1 is going to be a vector. And these are if we are looking at Cartesian coordinates, just to give you an example. So what you would typically do then is to calculate this for a set of values, X and Y. But you would typically plot it if you assume, and we are going to make life simple because we will look at the ground state only. And then we can assume that this is isotropic in space, so we don't deal with angles. So what we will typically do then is to plot this as a function of R. And in 2 dimensions, R is given by X squared plus Y squared. If you're in 3 dimensions, it's X squared plus Y squared plus Z squared. So we are going to assume, and this is okay for this Bose-Einstein case, assume that rho is isotropic, so it has no angle dependence. So this is just to make life simpler. And this is actually the case for the ground state of these harmonic oscillator bosons. So that means that what you need is a table of X and Y. So you can just set up an array of these values, and then you call this function. And that would return to you this rho as a function of X and Y. And then when you have this array, you simply calculate R, and then you can make a plot. So this is often the simplest way of doing that. Now, why do we calculate the one body density? So suppose now you made a plot of this function, and in our case, it's going to be isotropic. So we need only a scalar, rho, on R. So we are going to plot this as a function of R. So what you could get is something which looks like this. So this tells you the probability of finding a given particle in a specific position. That is what the one body density expresses. Because you see here, you have integrated away all the other particles. So what it means is that you're simply left with the probability of finding one of the particles in a specific position R. Now, the one body density is interesting because you can link that theoretically with charge distributions. So if somebody gives you a charge distribution of electrons in an atom or similar objects, then you can compare that with your theoretical analysis. Now, suppose this is the non-interacting case. And in our case, the non-interacting case is very simple. So you have a good test here. So in project 1, so let's non-interacting case, and you've been doing this again and again. Interacting case. This is just a function which has an analytical wave function. So this is just the harmonic oscillator. So when you calculate your wave function, or you calculate the energy for non-interacting bosons, then you can use as a test that your one body density is correct if you take the harmonic oscillator case, the non-interacting case, because then you know that the exact wave function is then proportional to e to the minus alpha squared times r squared, right? Except for normalization factors. So you can then compare directly with the analytical answer. You may have to tweak a little bit with normalization constants, but in principle, you have an analytical result which you should get. So that's very useful if you're a little bit in doubt whether you're calculating it correctly. Now, suppose now that you add interaction, and I'm going to give you two examples. So this is with interaction, but I could also get another result which looks like this. So this is very schematic. So this is also with interaction. And when I said that the one body density is extremely useful, because you would normally calculate the non-interacting case, and then you compare with the interacting case. And that tells you about the features of the interaction. So if you look at these two cases, what kind of property does the interaction have? So if you look at the expectation value, will it be larger than 0 or no, less than 0 or larger than 0? That means, let me just rewrite it. Let me just rewrite it in words here. So is this repulsive or attractive? So repulsive means that particles get repelled. So if you calculate the one, which one will you choose here? Or which one does your intuition say? Yeah, it's repulsive. So in this specific case, what we have is that this is repulsive. So the particles get pushed out, which means that your one body density, the likelihood of being close to 0 is getting smaller because the force pushes particle apart from each other. And then similarly, in this specific case here, then we would have an attractive or attraction between two particles because then they get pulled in. Yeah. Yep, absolutely, exactly. So this is a very useful theoretical measure, which tells you a lot about the interactions and the forces at play. So if you run an experiment and you can extract from experiment a charge distribution, which is just a one body density distribution multiplied with a charge, then you can actually look at your theoretical calculation and compare that with experimental data. And that can say something about the type of forces you have at hand. So here, so the one body density is not an observable. It's a theoretical quantity you calculate, but you can relate that one to experimental quantities like charge distribution, things like that. So it's an extremely useful measure of correlations. And it's something which can help us in getting some more intuition about what is going on. So what I was thinking of now is that we switch over to the optimization part. And Daniel is going to say something about Python, and then we will get back to the other part. So I'm going to pause the.
Okay. Yeah. So I decided to mimic very much what the process of the OpenMP or MPI parallelization would do, because we could, for example, in the Python computation, we could vectorize some operations, for example, in the optimization of the parameters and then parallelize that, right? But what we are doing with the OpenMP or the MPI implementation is not that. What we are going to parallelize is the sampling process, right? Because that can take a long time. And we want to run as many samples as possible, and then we get a better statistics from that. And in C++, you simply do a pragma OpenMP, and then you spawn different threads, and then you run independent processes in your computer, right? And then in Python, there are different ways of doing that as well. I think one of the most common ones is using this thing called the process pulse from pathos, but that's not what I'm going to do because we are using JAX. When I tried to do this parallelization process with JAX and with pathos, it gave some problems of related to the fact that when you are using multiple processes, you have in Python to serialize the data first. And the way to do that is by something called pickle. And what I found out by a lot of trial and error is that this thing called joblib, it uses something called cloud pickle, and that seemed to give no problem in the just-in-time compilation when we use the JAX, right? And the idea is pretty simple, but there was one of the things in the template that was missing, in the sense that maybe you guys would have to figure out a lot of stuff to do this. And now the current version of the template page in GitHub is up to date. So it has this individual file which was kind of missing. And I will show you what I had to do in order to make this work. And it will seem like a lot, but it's actually not, because most of the things that I did here, most of the different things that I implemented are actually what you guys probably already have done. The only thing that is important is this file which I added. And this file is under utils, and it's sampler utils. So just to show that the things work, at least in the parallelization part of the sampling. If you are using the template, your config looks something like this. And this change is exactly the number of Monte Carlo chains that you want to be parallelized, right? So let's keep it to 1. And I'm running the code with a lot of placeholder functions. So the results are not physical, but the thing runs, right? So it trained incredibly fast because it's not doing anything at all, right? And then it sampled with 1 chain, and here it collected some statistics, and it plotted it. And of course, these results here are none. So let's, for example, use 2 chains. So let's parallelize this, and let's see what happens. And okay, so then the sampling process was done in this parallelized manner. And the layout for you guys, I think, is already going to be kind of beautiful because of this the way that we are plotting with TQDM. I think if you guys are using the template, you will not have to worry about this beautiful plotting of the progress bars and things like that. But let's go to what actually matters. So I am going to show everything that I changed with respect to the repository, right? So let's minimize this here. So first thing here, I just added the set sampler, right? I'm just choosing which sampler to use. I think you guys probably already did something like this inside this function, because this on the left side, just to be clear, on the left side is exactly what you have in the repository. Okay, so this is a difference. Another thing is that I removed this placeholder for the results, right? So here I'm actually collecting results from sample. You guys probably already are using this if you are using this sample function, which was already there. And yeah, and this is just some commenting things out. So for this file, which has differences, is probably something that you guys already have. Here I just have some imports. I'm importing from sampler utils, which is the file that I just recently added, and some other things just to display stuff. Okay, so here is the part of the parent class sampler where you choose if you are going to use 1 chain or multiple chains, right? And this was already here, so probably you guys checked this function, which is check and set chains. It's also important from a utils folder, which I left there. And what it does, it's basically, it looks at the number of chains that you're asking. It compares with the number of CPU cores that you have. And if it's over that, let's say you have 7 cores and you asked for 10, it will reduce it to 7, just to make sure. And so this, again, is not something new. It was already there if you guys are using the template. Okay, so here comes the difference. Inside this function sampler, which is actually a helper, there is this quote unquote private, right? Because there's no private function and method in Python, but it's just a convention to use this underscore here in the function to say that it's a private thing. And this underscore sample is what each individual process is going to see. So in the case where we have only 1 chain, I simply call this private method and I extract the results from that. No problem at all. The only different thing is that when you use multiple processes, you are going to feed this function, this private function, to all of the individual processes independently, right? And the way that you do this is by using this function, which I just recently added there. So we have to go to this, where is it? Utils, sampler utils, multiproc. Okay, so this is the thing this is where the magic happens. We have first to set a individual seed for each of the random walkers, right? We don't want them to do exactly the same thing. You want them to start by from different places. Else you would have just the same result for each one of them. But also you have to give each of the processes the same picture of the data, right? And this is where a lot of the problems come with JOCs. But you basically just want to make a copy of each of the things that you're passing. So for example, the wave function object, which will carry all the parameters that you want to optimize and things like that. The state, the scale of the sampling. You want each of these things to be private to every process, right? And here is where I am using the job with parallel. So I created this another helper function, which is a compute, and each process is going to do this compute thing. And it's going to, this delay, it just means that it's going to return a generation, which will make the calculation as soon as it's ready, and it does not depend on the other processes being finished or not, right? So this is basically the line where it's doing this computation and it's parallelizing it. And you see that the number of jobs is -1. This means that I'm choosing the maximum amount of processes that I can. But remember that actually we are limiting this when we do this end chains, which was set by the function that's already there, the check and set chains. So we are doing this loop where we are accessing only the correct copy for the correct process, right? This is why in this compute, you have this index, which is telling which chain do I want to use. And this is why I'm accessing only the correct copied parameters that I want. So for example, each process will access its seed, and this will be different. The rest of the things, they will be kind of more of the same. They will be exactly the same, but we need to make the copy in this way, multiply by the number of chains, so that we have kind of a private copy of those objects. So as long as you use this function, which is already there, and run your sample in the format that was originally set in the template, I don't think there should be any problem at all. But if there are any questions with respect to that, please feel free to ask. It seems like a lot, but actually it's just one file doing the whole thing. Is there any question about that? Is something unclear? Okay. So from my side, that's it.
So let me then just switch back to the Jupyter Notebook. Or rather, before we do that, it's a little bit about the parallelization strategy here. So the Monte Carlo calculations are extremely simple to parallelize. So that means that when you look at parallelization strategies, it's very much like, for those of you who are familiar with parallelization strategies, it's like parallelizing the calculation of an integral. So when you calculate an integral, there is normally no dependence between the different small areas. So if you think of the strategies, so parallelization strategies, in essence, what we are doing is actually to calculate a multidimensional integral. So if you think of just an integral, suppose now you have your favorite method, which could be the trapezoidal rule, and you have to integrate a function like this. What you would typically do then is to split the domain in smaller boxes, like this, etc., till the end point. So you would have a beginning point A and B. So the standard parallelization strategy would be if you now have n integration points here, with n points between A and B, this would be to split this in a given fraction of points. So that means that every point here would have a local set of points. So you would have n local, which is normally given by the total number of integration points divided by the number of processes. So each process would then calculate its own contribution to the integral. And then when all the processes are done, you would simply collect the results and simply add things up. And then you have the final answer. Now, keep in mind that the number of CPU time, the CPU time you spend is always the same. So if you need 10 hours, the only thing you're doing now, if you have 10 processes, is that you would split 10 hours on 10 processes, and you would be done in an hour. So your waiting time is reduced from 10 hours to 1 hour, but the number of CPU hours you spend on a machine is exactly the same as before, except that you, instead of waiting 10 hours, you just wait 1 hour, and you would have the same result. So this is just a way to distribute jobs on different nodes and then collect the results at the end. So in our case, the easiest way to do that, or perhaps there are several ways, is actually to have a full calculation, full run for each process. For each, that's actually the simplest possible thing we can do. So that means that each full process is then for I equal 1 up to the number of Monte Carlo cycles, do something, and then it returns the energies, expectation values, etc. And then end for, and this return energy, energy squared, etc. to main process. So that means that this block, which you see here, is then done by each sub-process, or just each process. And if you have 100 processes going on, and you're running 1 million Monte Carlo cycles, that means that you will have 100 times 1 million, 100 million samplings of the energy and the other expectation values. And hopefully that gives you better statistics. Because as I said in the beginning, the Monte Carlo calculation is a data greedy calculation. The more, the better. So if you can then distribute the jobs and run many of these processes simultaneously, that will give you hopefully better statistics. So the basic strategy is then to just think of you dumping the jobs to each node and then just collect data at the end. So you would have some main process which sets up the communication between the processes. While the jobs are running, there is no need for communication. This is often something which is a bottleneck in parallelization, because if you have to communicate while the calculations are running, this can typically slow down performance for you. So a Monte Carlo calculation is, as I said, it's embarrassingly trivial to parallelize. And what you could do is, if you have a given number of cores on your laptops, you could just simply start the program on different cores and then just collect at the end. That's the simplest possible way. And other people have done, if they haven't had access to any high performance computing facilities, if there was a lab with, let's say, 16 PCs, you just logged in and you started the job on each PC, and then you waited till it was done, and then you just collected the result. That's the simplest possible way of doing that. And actually, in high-performance computing facilities, in the beginning, people did that. They just submitted different jobs. And then the people responsible for the facilities, they discovered that people were not using the high-performance computing parallelization tools, which they had paid a fortune for. You were just dumping scripts which were doing the same things. So in a sense, you were not parallelizing. So a Monte Carlo calculation like the ones we are running here are very easy to parallelize. So in the lecture notes, if we go back, so I would actually, this is the kind of recipe which we would suggest. You could obviously split your calculations here, but there will be dependencies. So you could think of, let's say you have 1 million cycles, you do the first 10,000 on one node, et cetera, but then you would have dependencies and you would have to communicate that. So the best thing is actually to run everything as one full job, and then you just collect the data. And everyone here produces your outputs, and that will then be used to process the final expectation value. So that's often the best strategy. And if we go back to the lecture notes, there is a lot of material. So we will spend some time in the lab sessions discussing that. And also many of you have taken the high performance, the parallelization course, which is called IN 3200 or 4200. Is anyone who's taken that? Okay, one of you has done that. And some of you will probably take that in the spring semester. So here you will find recipes on how to do that for C++. One of the things which we also recommend you to take a look at is about optimization and profiling, which can be very useful to look at before you start parallelizing. So much of what you see here is like a manual. And the best thing is actually to look at the manual, because the only thing you need to do is to add some additional instructions in your program. Whether you use MPI or OpenMP, so MPI is tailored to distributed memory and shared memory, whereas OpenMP is tailored for shared memory. So a typical laptop has 2 or 4 cores, so you could actually run 4 different threads or 2 different threads, depending on the laptop which you have. Or some even have 16 now, depending on how much money you've been willing to spend. And if you have GPUs, that's also another possibility. But we are not assuming that you have that. There are some instructions on optimization. So when you're compiling your code, we normally always recommend that you first compile with no optimization, so that you know that the program is translated into machine instruction and does exactly what you want it to do. And then when you're sure that everything is running correctly, you can add optimization flags like these ones, where you typically try to vectorize. Vectorization means that you're using the registers in a more efficient way, and you can do operations simultaneously. Typically, you can do 2 to 16 operations simultaneously, if you're adding numbers, for instance. And there are also other tools like the profiling options, which is extremely useful. So this PG here allows you to find out which functions are stealing most of the time. So you can, if you compile with that flag, it's going to be slower because it counts the number of times you call a function, but that can be very useful. So we had a case where we were actually wasting lots of CPU cycles on calculating binomial factors. So for those of you who are familiar with linear angular momentum algebra, there are some recoupling coefficients, which are called Clebsch-Gordon coefficients. Some of you may have heard of that. And that involves binomials. So one of the guys who was responsible for writing that was actually calling the calculation of binomials every time. And when we realized that that was the case, the time we needed went from 24 hours roughly to 5 minutes, because we were just calling a binomial calculation again and again and again. And that was seen immediately by this simple compiling options, which you have on basically your own Linux and Unix distributions. So that's something which we recommend. You have other tools like Valgrind, which allow you to study memory leaks, etc., which are very useful. So we would typically recommend that. And then we have hints, which are things to avoid. So if you have something like this, this is not the best way of doing things, because if you have a loop, as I mentioned before we started here, if you have 1 million terms in the sum, you're performing 1 million unnecessary multiplications. And this is the way you would typically do that. You define a variable here, and then you add it here. This is hidden for you often when you write it in Python, or when you use a library like Eigen or Armadillo in C++. But just be careful with some of these operations, because it's so easy to actually avoid them. There's a lot of information here, and this is something which I will not go through, but we will discuss these things. We can discuss these things in the lab. Here's a little bit about vectorization and what it means, and some small bottlenecks to think of. If you scroll down, you will also find a discussion of how to use MPI and OpenMP. So there's a lot of discussions about vectorization and another technicality. So I'm just scrolling down to the discussion of speed up and other things. But the easiest thing with, let's say, MPI, if you want to use that, you would need to install it on your laptop. And one possibility is just to go to the OpenMPI website, which is the one I would recommend. And then you would typically compile with MPI C++. And then when you run it, you have either MPI exec or MPI run. And this would be the number of threads which are starting. And this is very easy to do on your own laptops. So for typically, if you want to run OpenMP, which is excellent for shared memories, you would have the flag F in OpenMP on standard Linux distributions. And if you're on a OS X system, you would typically install this libomp by brew install here. And then you would compile with this flag here. So these are just different types of compiler flags we can use. And then there are also some instructions on how to install MPI for standard Linux distributions and also for OS X. And then how you would run it when you have it installed. I think now it almost comes by default in some of the distributions. So message passing, let me just scroll down. This is often one of the easiest things to do. So the typical commands you would need to set up is MPI init. You need to finalize. You need to communicate the size of the job and also which rank it has. So every process has a rank. And these ranks are used for the communication between the different processes. And it's common that the main process, which is the one which collects information from all the other ones, common in the literature before, this was often called in a very, how to say, offensive, had an offensive naming. It was called master-slave. And we don't use that terminology anymore, but if you go back in all the text, you will find this more, how to say, offensive naming. So there was a master node, which then collected from all the other processes. Now we just say main process, which then distributes the jobs. And this is done with these MPI commands. So this is what a typical way you would set it up. You would read from screen the number of MPI processes you want to do. So I'm just going to go quickly through this. And you would then initialize the communication by telling how many processes there are and which rank a given process has. And in this case here, there is no kind of ordering in the hello world. So every process would compete with writing first. You can order this in a better way. And then you have an MPI finalize. But for you dealing with an integration, the easiest thing to look at is actually this example here, which contains a calculation of the trapezoidal rule. And in that case, you would split your integral in different boxes, different areas. And you see here now, when we start it, we initialize it. So when you run the program, you tell how many processes are present. You communicate that. You communicate which rank a given process has. And then you can define the number of local integrals. And you will find also the local integration start and integration end. And then you have the number of processes here, which now defines the local integration number. And then when you're integrating now, you would have a local sum. So every process calculates the local sum to the integral. Like you would have in the Monte Carlo calculation, you would have a local process which does the whole job for you. And then there's a command which is very useful to look at, which is called MPI reduce. So that collects the local guys. And since you have a summation operation here, it sums the local guys and returns a total sum. And in this case, it's only one variable. You can transfer arrays. It's a double. And then 0 here stands for the main process. And that's the one which collects the information. And you see here, if my rank is 0, this is the only one which writes either to file or to screen what the final result is. So for Monte Carlo calculation, what you would need is actually initialize everything. And then you would let every job simply run happily by itself. And then you would have an MPI reduce, which collects the final result. And you will also find examples on how to use MPI for this kind of parallelization. The OpenMP is actually much simpler. But we will stop here because we are running over time a little bit. And I invite you to take a look at the information here, because there is enough information to get you all started with parallelization here. So you can just see this as just some few lines you need to mend in your code. And then you can actually parallelize it either with OpenMP or with MPI if you prefer that. So it's actually pretty straightforward. And that's why we invite you more to look at the notes and discuss with us in the lab sessions. That is much better than just me preaching here. Because the philosophy of parallelization with Monte Carlo is so simple. I mean, it's just you running many jobs in parallel and then collect information. And these libraries, so this is not hardware, it's actually a library. They set up the communication between the different processes. That's the essence of these libraries.